Hello everyone and welcome to the volume of solids of revolution. We're going to take a look at the disk method first. In the disk method, what we are doing is we're taking a curve typically and we're going to be rotating it around a given line or an axis to create a 3D shape. So we're going to start with the most basic example first, and if I was to take a rectangle. Now obviously we use more curves, but just to get the idea of in the first visualization that we're going to need to do, we're going to start with the rectangle. If I was to revolve this around the x-axis, this would make this cylinder here. And in order to find the volume of the cylinder with a radius of r, okay, we would get that the volume is equal to pi times my radius squared. That gives me a circle. And if I take a whole bunch of these circles that make a thickness of dx, that would make a 3D shape, which would then make the cylinder. So what we're doing is we're looking at this volume as an accumulation of circles. We're just going to keep taking circle, 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 piling those up, and making a cylinder out of them. Now we could rotate a few different ways. This first example gives you a picture of a horizontal axis of revolution, and personally I think these are a little bit easier. They're more what we're used to visualizing. When you want a horizontal axis of revolution, such as the x-axis or a y equals line, y equals 1, y equals 2, something like that, we're going to be using a y equals equation. So y equals x squared, something like that. And in order to have something like that, okay, it gives us our equation in terms of x, which is what we're used to. And we would say that volume is equal to pi. We can always take a pi out because pi is just a number. We're going to go from A to B. Now this will be your intersection between 2 points, or it could be where a curve crosses the x-axis, but those are your start and end, left to right, just like we have been. Our radius in terms of x squared dx. If we were to look at this as a horizontal axis of, or excuse me, we did vertical. Excuse me, we just did horizontal. Vertical axis of revolution. The part that makes this a little bit more difficult to visualize is that we're going to have x equals equations, something like x equals y squared. We're just not as used to thinking about what that looks like, and so it can be difficult for us to think of how that would look. So if I wanted to go around the y-axis, I need to have my equation with a y as the input. So again, my volume is still going to be volume times pi, and I'm going to go A to B. And we're going to do our radius in terms of y squared dy. So one thing I hope that you can see and remember is that y-axis means I need a dy, x-axis means I need a dx. So if we look at this next example, this is at the bottom of the page, but this is the second page in my Smart Notebook. The most important word here is this idea of perpendicular. The rectangular strip, or the radius of what I'm revolving must be perpendicular to the axis of revolution. So, if we use this curve as an example, I'm revolving around the x-axis, so that's right here. And by having an f of x, or an equation in terms of x, this gives me a y value, so it gives me a height above the axis. And you can see that if I draw in those two lines, it makes a perpendicular symbol. So in this specific example, we're going from 0 to 3. So since I'm going from 0 to 3, here's my 0, here's my 3. And I'm going to go up and over the, we're talking about this part of the curve. And so if I was to revolve that, you can kind of see it would go somewhere like this. It would make something like a Hershey's Kiss type shape where it's like fat on the bottom and got a point on one end. So if I think about what makes the radius of this revolution, the radius comes from this line right here. That's my radius in terms of x. That also happens to be the curve. So as I go to set up my volume, pi, okay, from beginning to end, left to right, 0 to 3, and I'm going to have negative x cubed plus 3x squared dx. So it's really, really, really important that we don't forget that squared. Okay, this squared out here makes all the difference in the world. So let's go ahead and open up a graphing calculator. If you don't have one, pause the video and go get one. Okay, and I'm going to hopefully be able to do this on the screen. So I'm going to go to my Y1 and put that in, simply because this calculator is a little bit more cumbersome on the input than some of the newer versions that some of you have. Okay, so I have my equation in Y1. I'm going to put pi times math option 9, and this is where I'm going to put in my vars, y-vars, y1, so I don't have to type it, but I do need to square it, comma, in terms of x from 0 to 3. And so this gives me a volume of approximately 65.435, and it would technically be units cubed. You don't have to put this units cubed unless it's asked for. So that's kind of the idea of what we're doing. Let's do a few more examples. So if I wanted to rotate this, the first thing that I need to do is I need to draw myself a very rough sketch of what I'm talking about. Okay, so negative 1/2 x squared plus 2 is going to be a fat parabola that comes up at 2. Then it also gave me x equals negative 1 and x equals 2. So I'm rotating this part. Okay, and so the reason why they gave me the negative 1 and negative 2 is so that when I set it up, I have my beginning and end. So my volume is going to be pi. Okay, it's always got that pi out front because we're using circles. Okay, so it's going to be pi, and then I'm going to go from negative 1 to 2. My radius is the curve. So if I look at drawing in a radius of this revolution, that would be this right here, which is the distance up to the parabola. So I'm going to put 1/2 x squared plus 2 in as my radius, and then don't forget you need to square your radius, and then I'm going to put a dx. So if I wanted to do this on my calculator, the first thing I'm going to do is I'm going to change what's in my y1. So I'm going to clear that out. I'm going to put 0.5x squared plus 2. Okay, so then when I go to my home screen, I can go second enter to not have to retype them back in. I'm going y1 again is my radius squared in terms of x, but this time I'm going negative 1 to 2. And I got 61.732. So this is approximately 61.732. Always 3 decimal places. Okay, so now let's try the dreaded y-axis. Okay, so if I have a y-axis, the first thing I know I need to do is I have to rewrite my equation that was given to me in terms of x. So find the volume of the solid form by revolving the region. They're talking about this gray region. Okay, and so we're talking about this being my radius of revolution. So with that being my radius of revolution, I need to set this, I need to get this as an x equals. So I'm going to go ahead and square both sides. Okay, and then if I do y squared minus 16 is equal to negative x squared. If I divide by my negative, I'd get 16 minus y squared is equal to x squared. And then I would need to take the square root. Because we're in quadrant 1, we're talking about the positive. So x is going to equal this positive 16 minus y squared. If we had been in quadrant 2, we could have used the negative. So this radius right here comes from this length right there. So as I'm looking for my limits of integration, we know we're going to have pi, and then I need to put my limit, bottom 0, top 4, 0 to 4. 0 to 4, and then my radius becomes the square root of 16 minus y squared dy. So as I go ahead and put this in my graphing calculator, again I'm going to go to y1, I'm going to clear that out, the square root of 16, and when you put it in your calculator you input it as x because your calculator cannot do y as an input, so we just input it as x. Second, enter brings it back up for me. So I'm going to go 0, 2, 4. I get 134.041. So this would be 134.041. Okay, one last example, shall we? Okay, so when I look at what curves I've been given, I see that I have this curve, this xy equals 6. And I know that I'm going about the line x equals 6. X equals 6 is a vertical line. So because this is a vertical line, I'm going to rewrite the first equation as x equals 6 over y. Okay, so as I go to draw in what that would look like, I have this, 6 over 2 is 3, 6 over 3 is 2, 6 over 6 is 1. It kind of comes in this way. So I'm just kind of drawing in what I have. Y equals 2. Y equals 2 is right here. X equals 6 and y equals 6. So y equals 6 is right here. So if I look at the area that's in between all of that, I'm talking about this chunk right here. Okay, so now that I have, I think I did that correctly, right? I believe so, because I have y equals 2, y, which is here, y equals 6, x equals 6, and then I have this one. So I have the picture correct for those. So as I look at what I'm doing, the line x equals 6, that's this one. So this is where I'm rotating this around, and it's going to make almost like a bowl shape. So as I draw in my radius, the radius would have been 6 if it went all the way to the y-axis, but it didn't. It's short this chunk, and that chunk that's missing comes from this curve. So my radius is going to be 6 minus 6 over y. Make sure I square that. As I look for bottom to top, my limits of integration are going to be 2 to 6 because this comes from 2 to 6. I can't forget that I need a pi out front and a dy at the end. So as I look at this, I am going to change my y1 to 6 minus 6 over, and I have to use x because my calculator can't handle y as an input. And so I'm going to do second enter. I still have y1 squared, except now I'm going from 2 to 6. So this gives me approximately 241.588. Okay, we have one last example for this specific video, so let's talk about the line y equals 6. If we were to go about the line y equals 6, right here, I have the intersection at 1, that's the point 16 on the first curve, the hyperbola, this one. And it goes up until 6, because this is the area that I'm rotating. So it's going to go this way, and it's going to make a different shape because I'm rotating it differently. So if I look at what my axis would have been, my axis changes a little bit. And so I'm actually going to erase some of this coloring in here and draw it again, simply so that we can take a better look at exactly what I'm talking about here. So quickly drawing in some stuff. So I have the point 61, I have the point 2, 3, 3, 2, and 6, 1. So this is that 6 over x or 6 over y. It's that one right there. Then when I look at y equals 2, y equals 6, and x equals 6. This rotating around the line x equals 6 gets a little complicated because as I'm rotating it here, we still are going 1 to 6. But if you draw on your radius in different spots, my radius right here is 4. There is no curve to this part of the line. This is just a rectangle of 4. And that starts at about 3, because at 3 I have the point 32 on my rational function curve right here. So when I'm doing this, I am going to need to take that into consideration, because if I was to look at, say, this part, that has a different radius. When I draw in the radius of that part, okay, I am looking at this bottom, and so it would have been 6, but each part of this is missing that rational function curve. So, pi, and I'm going from 1 to 3 because that's the part where I'm affected by the curve, and my radius there is going to be 6 minus 6 over x squared dx. Then if I look at adding in the other part, this part that had a radius of 4, I'm going to go from, don't forget your pi out front, 3 to 6, and then my radius is 4. It never changes. It's always 4 squared dx. And so again, you can pause and put this in your calculator. I do have my notes where I've already done this. So I'm going to put this all in one step where I have this plus that. I can show you that quickly, I guess. So since this is already in y1, I'm good to go. I am going to go to y2 and put in 4. Okay. So on my home screen, second enter. That first integral only goes from 1 to 3. And then I'm going to go plus pi times math 9, and then my function is in y2. So vars over enter, it's in y2. Don't forget to square it, and that goes from 3 to 6. Oops, I have a syntax. What did I do? Oh, I forgot x, 3, 6. There we go. And so that gives me a total area of 203.889.